Okay, thank you. So, I mean, as I said yesterday, what I'll try to do today is to explain to you how the setup that I described yesterday, how this is already enough to reprove the Bernoulli theorem for curves on K3 surfaces. But I mean, before I go towards Bernoulli, I want to say a little bit more about stability conditions on K3 surface. So basically explaining Bridgeland's results on these a little bit. So on K3 surfaces, so I mean, just as a general theory, this is all due to Bridgeland. And right, so for today, X will always be a smooth projective K3 surface. And except for some side remarks, I'll assume that the Picard rank of X is equal to C dot H, just to simplify the discussion a little bit. Right, and I mean, I'll always use my lambda from yesterday will be this the algebraic homology. So the algebraic part of the Mukai lattice with the Mukai pairing, and the churn gets replaced by the Mukai vector. Churn of E times the square root of the tot. Thankfully, I don't have to try to write on a formula, thanks to François, with the pairing that I can just define by V of E paired with V of F is equal to minus the Euler characteristic between E and F. And right, and so when I'm in this assumption, then I can replace my polarization and this B field B by just multiples of this polarization, of course. And so I'll just use alpha and beta to in my notation. So this I'll get sigma alpha beta. That's the stability condition whose heart is given by co-beta of X. So these are these two-term complexes, this abelian category of two-term complexes that I described yesterday. And Z alpha beta, this is now slightly different, so let me write down the notation here. This is Z alpha beta of E. So with this Mukai pairing, it's actually more natural to write it as this. I pair V of E with E to the minus I alpha minus beta times H. And this is almost the same formula as yesterday. It gives a little bit more freedom.
So D is what?
Where's D?
Replace H, B by?
Alpha H and beta H. Right, so here for
What was B?
B was this B field that right, that I used to twist the churn character by. Right, so this field.
What is coherent B time?
So this was this. Yeah, maybe let me remind you of this. So co beta of X. This was this category of two-term complexes. So where you slope stability with respect to H, and then I take everything of slope bigger than beta, and everything of slope less than or equal to beta shifted by 1. Yeah. Okay. And somehow maybe maybe the most important theorem in the whole setup is a generalization of what already appeared in François' talk just now. So, I mean, there are many names to name for the classical case, and then for the case of Bridgeland stability condition, let me add Bridgeland and Toda. So I fix V in n of x primitive. Right, then I have this moduli space of Giesecke-stable sheaves. And of Mokai vector V. But I can also look at there's also a moduli space of stable objects. Right, so this is the moduli space of E in co-beta of x that are Z alpha beta stable in the abelian category. And I mean, the fact that such a moduli space even exists, this is work of Toda. And then the statement is that both of these are non-empty if and only if V squared is bigger than -2, greater or equal than -2, and their dimension is again the expected dimension. Right, and so, I mean, in a way, what is this saying, right? So we already know for alpha fairly large, these two spaces are the same, because these sigma-stable objects are exactly the Giesecke-stable sheaves. So basically what this is saying is that as we vary alpha and do wall crossing, we are neither destroying or we are never changing whether moduli space is non-empty, and we are never changing its dimension. Okay, and right, and somehow this is both. I mean, this is both. To relate this to yesterday, the statement is both stronger than Bogomolov Giesecke. Plus, it gives this support property. Did I label with 3 in the last talk? But I also want to say a little bit about the space of stability conditions. So I mean, one can introduce a topology on the set of all stability conditions, and this becomes the set of stability conditions on X becomes a topological space that I'll call by stab of X. And then I look at the connected component. This is just a connected component containing these sigma alpha betas. And then the theorem is that we can actually describe the space fairly precisely. So the statement is that not only is this a topological space, this is a complex manifold. And note, I mean, of course, there is a very natural map from the space of stability conditions to a vector space, namely the vector space of central charges, right, that sends the stability condition C A to Z. So the claim is that, so this is all still part of the theorem, this is a covering of its image. And I can also describe the image. And so the image is given by saying that this Mukai form restricted to the kernel of Z is negative. Then there is some orientation condition. So I won't make this precise, although I mean, if you thought about periods, then you can probably guess what this is. And the last condition is just that kernel of Z does not contain any -2 class. Right, and so let me explain the geometry of the statement. Right, so we are in the case of. Let me assume now. I mean, this statement is actually, so this statement is general. This doesn't depend on Picard rank 1. But let me draw the picture for Picard rank 1. Right, so then n of x has rank 3, and the Mukai pairing has signature 2, 1. So what I'm drawing here is the negative cone. And inside this negative cone, I have my roots, the -2 classes. Right, and so the statement is that I can vary my central charge freely as long as the kernel A stays within this negative cone and does not hit any of the -2 classes. Right, and in other words, I mean, to relate this to the previous theorem, I can vary my central charge freely as long as I'm ensuring that no stable object, no Mukai vector of a stable object gets sent into the kernel or close to the kernel. Right, so all the set here is up to rescaling is densely populated with Mukai vectors of stable objects, and then I have the spherical objects that are stable, and as long as I'm ensuring that these are not get sent to 0, I can vary my central charge freely. Right, and so I mean, in particular, I mean, up to homotopy, this is really just a covering of the unit disk with some infinitely many holes removed. Here, for every line bundle, for example, I would have to insert a hole. And then let me also explain in this picture what the support property is. The support property just is the observation that, I mean, whatever this kernel is that satisfies these conditions, I can always find some small round cone around it that still doesn't contain any Mukai vectors of semi-stable objects. And as a side remark, in general, we don't actually know whether stop dagger of X is simply connected. So this is only a theorem for Picard rank 1. Right, and so when I talk about wall crossing, what I mean really is fix some V, so that I'm looking at all the moduli spaces of objects of fixed class. And then when I walk around the space, then for small deformations, the moduli space won't change, but sometimes I'll hit walls where they're strictly semi-stable objects, and then when I cross the wall, the moduli space will change. Okay, but I mean, so much for the general theory. Now I really want to use I mean, even though I don't, right? So, I mean, for the rest of today, you can actually again forget this picture. I mean, I wanted to state it because it's a complete picture surrounding what I'm doing. But for the rest of today, again, I'll just need these geometric stability conditions that I constructed yesterday. Okay, any questions so far? Okay, so then let me just remind you briefly about Brunner, right? So if C is a projective curve over C, and then G is the genus of C, and I given D and R, so I'll use slightly different than standard notation for a reason. So V R D of C, these are all the line bundles of degree D that have exactly R plus 1 sections. Right, and the question of Brunner theory is, of course, I mean, is this non-empty? And what is the dimension of this when it's non-empty? And let me also remind you of the Brunner number. So rho is rho of RdG. I'll abbreviate this as rho. This is G minus R plus 1 times D minus G plus R. And so this is the expected dimension of VRDC. And the theorem that I reprove for you today is the following. So again, X is a K3 surface. And now let me assume that it has peak rank 1, and I take a curve in the primitive linear system. Then the dimension of VRD of C is equal to the expected dimension. Right? So any curve of primitive class on a K3 surface of peak rank 1 is Brunner general. Okay, and so, of course, going to use wall crossing. I'll fit this into the moduli space, and of course the natural moduli space to consider is the relative bicarority of this linear system. So let me just make one assumption from here on now, which is that D is less than or equal to G minus 1. I mean, one can, of course, always reduce this case. The proof I'm going to present would actually also work in the other case, but then, to be honest, I would have to use just a little bit more of derived categories technology, and this way it stays a little bit more elementary. Right, and so I said V equal 0 HD plus 1 minus G, and then MH of V is a compactification of the relative bicarority over this linear system. If pick D going down to the linear system, and over curve C, here I have pick D of C. Okay, and let me also remind you that, right, so MH of V, this is the same as M sigma alpha beta of V as alpha is sufficiently big, no matter what the beta. Right? And so what I'll do is I'll study wall crossing for this moduli space. So I'll move my stability condition around in this picture and see how this space changes. And I mean, in a way, the point of my talk is that just studying this wall crossing precisely essentially automatically forces you to reproof Bernoulli. And some of the wall crossing also reproofs the Bernoulli for you. Okay, so what's the first thing I want to do? Well, I want to study the first wall that I hit when I mean, say this large volume limit is somewhere here. So I walk away from this. What is the first wall that I study? And this proposition that's actually, so maybe I should say here, not wall crossing, but first wall crossing. And it's actually literally the first wall crossing in the sense that was the first wall crossing someone studied in detail. This was first, I mean, slightly more special for D equal G minus 1 study by Akara Bertram 10 years ago. So essentially, this was the first wall crossing paper. And all I'm doing is I'm looking a little bit more detail at the same situation. Okay, so let me assume that beta is a very small negative number. And then I let alpha go to 0 from infinity. And then they claim the first wall, as alpha decreases, is given as follows. So the L in MH of V becomes semi-stable if and only if it has a global section. And the destabilizing short exact sequence this one is given by OX plus H0 of L goes into L. Right, so I keep writing L even though L might not be a line bundle, it might be on the compactified part. And then the quotient here is, let me just call it E, E is equal to the shift of this Lazarsfeld-Mukai bundle when L is globally generated. Right, so the statement is that I'm making is that, in particular, is that OX is still stable at this wall, right? And in a way, right? Yesterday I made claims that this abelian category helps you to understand cohomology classes as morphisms and make this more elementary. In a way, what I'm doing today is even more elementary, right? I'm taking the most natural map I could possibly have. I take a global section of a line bundle. And but still it's helpful to reflect what this construction gives me in addition. Well, the point is that if I look at in the abelian category of semi-stables of the same slope, then OX is a simple object in this category. And that means that this morphism here is automatically an injection. And this quotient here, E, is automatically semi-stable. Right? It's automatically semi-stable with respect to this stability condition. So this is really the additional input that and that makes it, I mean, this line bundle ML even more useful than usual. Or in a way, this is the additional input compared to Lazarsfeld classical proof, right? And so ML, yeah.
So you mean that these semi-stability
Yeah, so sorry. I mean, this is at the wall. So at the wall, I have z of ox here, and z of ol, z of l, and z of e. They all point in the same direction. Yeah. And then when I cross the wall, it really becomes unstable.
Sorry, but I think I'm missing things completely. So you have this OX plus H0 of L, which injects into L.
Yes.
Then you have ML, which is the kernel of the projection of the thing.
So So this is a short exact sequence in this new abelian category here. Whereas here, I mean kernel with respect to the usual category of coherent sheaves. Right? So in the category of coherent sheaves, this is typical surjection when L is globally generated. And now in this category, instead, this map is always an injection. Right?
So ML is the category of coherent sheaves?
Yes, ML is a vector bundle. That's the. Yeah. Yeah. Thanks. Right, and so let me just point out an immediate corollary from this one. Right, so maybe let me introduce some notation here. So let me use W to be the Mukai vector of ML, which of course I can compute, right? This is just my original V minus R plus 1 times V of OX. And then it's an easy to computation to see that W squared is exactly twice the Brown-Noether number minus 2. So in other words, the moduli space, the dimension of the moduli space is equal to twice the Brown-Noether number. Right? And so, for example, this immediately gives you as a corollary that when the Brown-Noether number is empty, then this whole Brown-Noether variety is empty. Right? Just because this quotient here cannot exist. I mean, this quotient would have to satisfy, I mean, all the Jordan-Hölder factors would have to satisfy the assumption of my theorem, and then it's an easy check to see that this also would hold for W itself. Right, so this theorem immediately gives us the emptiness of the Brown-Noether locus when we expect it to be empty. Right, and to get the full result, we have to be a little bit more precise. Right, so more precisely, I have to prove two lemmas. So lemma 1 is that. Right, so let me use sigma wall for the stability condition where this kind of thing happens. So one has to prove a small lemma that I mean, if I look at the stable objects at the wall of class W, then that still has the same dimension, right? There's an open set of objects that remain stable at this wall. And right, and I mean, the kind of arguments that one needs, it's really a very elementary lattice theorem, because I mean, all the Jordan-Hölder factors would lie in the rank 2 lattice generated by W and V. And basically, it's easy to check that if you have an object in here, then there isn't much room in the simple lattice for further decomposition into stable factors. And then the second lemma is the following. So given an M in M sigma wall stable of W, so an object in here that's stable in the wall, and a non-trivial extension and here by non-trivial, I just mean that there are no morphisms from E to OX. Right, and then clearly this E then clearly this E is semi-stable at the wall because all these objects have the same phase of class V. But it's actually easy to check that it becomes stable if you move off the wall in the right direction. Right, so and becomes stable off the wall when we increase alpha. As alpha increases. Right, and so this is an elementary lemma for essentially for this category of semi-stables, but this immediately implies, combined with the previous observation that this is the first wall, this immediately implies that E is actually one of this rank 0 torsion sheaves. No, so within this, I can also do this for this kind of stable objects, right?
What is your filtration? Which?
Right, so I have this abelian category co-beta. I have this abelian category co-beta. And on this I have a notion of slope.
Yes.
And then I just mean Jordan-Hölder factors with respect to this notion of slope. So it just means that
Factors, what kind of objects are
they? They're again objects of co-beta. Right, so they are stable objects of the same phase. That's and any semi-stable object has a filtration where all the filtration quotients are stable.
W are vectors. So what does it mean?
I see. Sorry, I would have Mokai vector in.
And saturated with respect to what?
Right, so this is these generators sublattice of the algebraic Mokai lattice. And I just take the saturation there. Right, so the point is really that this is a purely numerical computation, so there's no room for Mokai vectors of Jordan-Hölder factors. Right. Okay, so if I just restate the last two lemmas, what this actually means is that the VRD is the right. So, sorry, I'm not sure I had introduced this before. By this I just mean the union over all C in the linear system of line bundles with exactly R+1 global sections. Then this is equal to a Grassmannian of R+1 planes, where that basically parameterizes these extensions. So there's some vector bundle E. So E vector bundle on MW stable, M sigma wall stable of W that's given by, E restricted to some M is just the x1 from M to OX. Right, and then, of course, we can, since these two objects are stable of the same phase, we know there are no humps between them either way, so the x1 has exactly expected dimension, so we can compute the rank of this bundle, and so we can compute the dimension of this Grassmannian. Remember, we also know the dimension of this moduli space. So the dimension, one just does the computation, and one gets the expected number, rho plus g. And so it's a g-dimensional family, and so I would expect this to have rho plus g as dimension. So in a way, I've already proved Bernoulli for the family, and now I want to deduce it for the individual curves. Right? So how do I conclude from here? Well, now I just need to use a little bit more geometry of holomorphic symplectic varieties. Right, because by now the setting has become very geometric. I have here this MH of V, which is of course holomorphic symplectic by Bouville-Donati, and it has a Lagrangian fibration to PG, the linear system, just by sending any sheaf F here to its support. And inside here, I have this VRD this Grassmannian bundle over MW. And if I intersect any fiber here with anything in here, then what do I get? I exactly get those line bundles of global sections R+1 that map to a specific curve. So in other words, I get exactly VRDC. So if I take a C in here, and this is pi, then here inside here I have VRD of C. This is just the intersection with pi inverse of C. Okay, and of course this is a Lagrangian fibration, so the symplectic form vanishes on the fibers. Okay, and so now I'll just play with the geometry of this one. And so the first one is that, of course, we know exactly which curve gets contracted by pi. Right, so in a sense, pi is not birational, but other than that, it looks like an extremal contraction in the sense that there's only one curve class that gets contracted here. So, so we know the curve class, the class of curves contracted by pi. And it's not one can check that it's not proportional, right? Remember, again, this was a Grassmannian bundle. One can check that it's not proportional to the class of a line in this Grassmannian. So not proportional and from this it means that, I mean, if I take this map and I restrict it to here, then Q cannot contract any curve. Right, because such a curve would be proportional to the class of the line integral Riemannian and proportional to the curve class contracted by here. Right, so in other words, so the dimension of VRD of C is equal to the dimension of Q, of its image under Q. And now the second one needs a little bit more. So if I take the symplectic form and I restrict it to this Riemannian bundle, then this is actually pulled back from MW. And so this is maybe the most powerful ingredient here. And now remember that, I mean, this is a subvariety of a Lagrangian fiber. So in particular, the symplectic form vanishes here. Right, and so from this, and so combined with this, we know that the pullback of the symplectic form from here restricted to here vanishes. Right, so in other words, Q of VR dc is isotropic, so the restriction of the in MW. So the restriction of the symplectic form here to this image is 0. And so from this it follows that the dimension of Q of VR dc is of course less than or equal to 1/2 the dimension of MW, and this is exactly the Brill-Newton number. Okay, let me stop here for today. Thank you.